Welcome, everybody. My name is Antonio Castro Neto. I'm the director of the Center for Advanced 2D Materials at the National University of Singapore. Welcome to the C2DM Homely Atmosphere online seminars. So this series of seminars was created with the objective of bringing people together to talk about science and things related to graphene and 2D materials in these very strange times we are living in. And every week we're going to have one speaker who is going to talk about a topic of his or her interest. And today we start this series with the right foot, with Professor Konstantin Novoselov from the Material Science Engineering Department at NUS. And Kostya is going to give a talk about Ballistic Hall magnetometry. So the way this is going to happen is that Professor Kostya is going to talk for around 40 minutes, and then we're going to have time for questions. You can ask questions through the Q&A button on your screen. And with that, I want to welcome Kostya. Thank you, Kostya.
Great, thanks a lot, Antonio. Let's try to share the screen back and screen 2. So can you see it? Hello?
Yes, yes.
Okay, great. So thanks a lot, Antonio, for this opportunity. It's bloody busy here in the lab, but still an interesting experience to give a seminar in such a condition. And the topic for this talk is it's something I really wanted to do for quite some time, and it was motivated by a recent paper by Min-Soo Kim. You will see it later, but also motivated by a present which I received some time ago from a good friend of mine. So he is a very interesting person, and he is a part of everything else. He is a keen archaeologist as well. And we used to go to various mines together with him. And once he gave me a sample, a specimen, as you see on the screen, just for me as a present. So not exactly this one, but very, very similar. And for me, this specimen actually is quite remarkable, because it really signifies the two systems which I really like and love and been working for quite some time on. So what is this specimen? It's garnet, those red crystals which you see. It's garnet in graphite, and it's quite a rare combination. It's found in only one mine called the Fat Boy mine in US, and it's actually not very expensive, but I'm quite lucky to have one of them. And I'll try to show you how these two minerals, graphite and garnet, which have quite a rare combination, but how they work together, or in my career, and why they're so important for me. So let's start with go back to the title and talk a little bit about magnetometry. So generally, how do we measure magnetic field? There are many different ways how do we do it, and it all really depends on the scale, maybe on the temperature range you want to do it. And there are many different magnetometers available, and they're being utilized on a huge variety of scale. So one One example is just our linkage to the back to the archaeology is the magnetometers which are used by archaeologists, maybe smart archaeologists who use this differential magnetometer to investigate anomalies in the magnetic response from the from underground. So through this, just simply by walking back and forth and recording the magnetic signal, they can cover quite a large area. So in this case, it's more than a kilometer, and they can really get quite a remarkable information from this. So here is the example of a field in Somerset, and you can see those usual Stonehenge-like stones arranged in circular patterns. But if you investigate the same site with the magnetometry, you actually see much more, and you can see many more spiral rings, and people managed to reconstruct much more elaborative structure at this place, which they date back to 1500 BC. If we go to an opposite range, so there are many ways how to measure magnetic field on the microscopic scale. Here is one example when we go from Romans to study metabolites, basically the output of the life of those bacteria is the magnetic bacteria, and they transfer minerals into magnetic nanoparticles. And one of the interesting way and conventional way how to study the magnetization of those nanoparticles is through the TEM in the transmission electron microscope, where they use basically Aharonov-Bohm effect to get they measure the phase of the electrons. So those stripes which you see is the interference pattern for the electrons, and they can convert it into the magnetic flux and extract the magnetization information from this. Now, what I want to present is maybe a little bit more mundane, but also definitely much more practical way how to measure magnetic field. It's through the Hall effect. Basically, if you send current through any conductor, and if you apply magnetic field, then you can measure the transverse voltage, which usually called the Hall voltage, and this Hall voltage is proportional to the somehow proportional to the magnetic field, and it depends also on the concentration of the charge carriers as well. Quite a convenient way to use it for the magnetometry is to utilize the two-dimensional electron gas and in gallium arsenide, aluminium gallium arsenide heterostructures, so 2DAG, and so you can create Hall probes of pretty much any shape and any size, as you can see on the picture. So here you send current like this, and you measure Hall voltage on those five crosses, and you can extract the information on the magnetic field within those crosses. Of course, the interesting thing would be not to measure just the external magnetic field, but the good question would be, what if you place some object of interest onto your Hall cross? Can you extract any reasonable information about the magnetization of this object? And the answer is that in the general case, the response, the Hall voltage response, would be quite a complex function of the magnetization the object. But in a specific case of ballistic transport, when your charge carriers don't scatter at all within the size of this cross, the answer is that your Hall voltage is proportional to the average magnetic field within this Hall cross. So basically, if you measure the Hall voltage on the ballistic junctions, then you can convert it directly into the flux. In a sense, your Hall cross acts as a tiny squid with quite a decent sensitivity. And the advantage, of course, of the Hall probes is that they can be operational at a very broad range of temperatures, and the sensitivity is actually quite comparable to the squid. So the typical sensitivity you can get is about 10⁻³ of the flux quantity. It's about 10⁴ of the Bohr magnetons, and in principle it can be improved even further if you go into smaller devices, which generally a bit difficult with the 3,5 with gallium arsenide heterostructures because of the depletion with the depletion length. But it would be quite possible with graphene, and that's why we were quite excited to transfer this technology to graphene, and I'll talk a little bit later about this. And of course, it would be interesting to see if we can get at the end, if you can get to the fundamental limit of the single Bohr magneton. So let me start from some historical overview. So this technique was pioneered by several people. Probably Andre Geim was one of the first people to work on this. Definitely, he created most of the engineering experiments. So he was pioneering to the use of this technique to study the magnetization of the mesoscopic superconductors, for example, aluminum disks, and there you can immediately see such effects as, for example, flux going in, going out of this of those aluminum disks. You can count the flux. You can see some magic numbers of the flux when they create certain stable structures. You can see the negative vortices where you can because of the surface superconductivity. So it was extremely successful application of this technique towards the study of the mesoscopic superconductivity. So equally interesting it was to apply it to study the magnetization of the ferromagnets as well. So here is an example of such Hall probes applied to study magnetization of dysprosium pillars. I should say it doesn't really work well with the dysprosium because the saturation magnetization is huge, and basically what happens that your electrons get trapped in a magnetic trap under those pillars, and you break down the Hall effect. But it would be very, very good to study weaker ferromagnets. So it's quite easy to study strong ferromagnets. It's much more challenging to study ferromagnets with weaker magnetization, and that's why we applied this technique to study the magnetization of the yttrium iron garnets. And here is a picture of such a garnet. So it's really a beautiful material. So now we are going to the first material from those minerals, those red crystals, the garnet crystals. But here we work not with the bulk crystals, but with the thin films of yttrium iron garnets, and those thin films they would typically have, depending on the thickness and the growth conditions, they would have uniaxial anisotropy, and in the optical microscope you can apply the Carey effect, and you can see domains of opposite magnetization as different colors, and you can see here so that those domains would be would have quite a distinct width, and they form quite an interesting pattern. Actually, depending on the particular arrangement, you can get very different types of the domains and the domain walls. So here is another example of the garnet film with the uniaxial anisotropy. So it's so-called undulating domains at the surface. They branch like this. This is an MFM image, and I think I won some image competition a long time ago with this particular image. But again, depending on the growth conditions and on the thickness of the film, you would get many different domain configurations, which you can study either with MFM, for example, or with the beta decoration technique, and you get very interesting patterns out of this. So why actually it's interesting why there is such a variety of those garnet films available to us, and the reason for that is that at certain moment they were used as a commercial memory devices. So under certain conditions, you can create those domains into a bubble phase, as you can see on the image, and then you can manipulate those bubbles and basically send them in a chain train in a memory chip. And it was basically a commercial memory chip at certain moment, until, of course, I mean, it's quite stable and quite robust. The bad thing about them, that those domains are, of course, huge. They're of micron size, and it's very difficult to make them smaller. So at a certain moment, this technology became obsolete. But we were lucky; we still catched some of the samples which were grown on the original Philips machines, and those samples, they were extremely clean with very low pinning, and it was a huge pleasure to work with them. So what you can do with those garnet films, well, if you apply external magnetic field, what you see that you can promote the certain magnetization of the you make one magnetization more preferable than the other, and basically domains of this magnetization start to grow, and the domains of the other magnetization start to shrink, and you can think about it as the domain wall between those two sides, moving across, moving in between of those domains. So what you see on this picture is the MFM sequence of images, and as we apply quite small magnetic field, and you can see that the domain walls move back and forth, and the domain wall, the configuration of those domains would change slightly as you shrink them entirely and start to grow them again. So the type of the sample we used to work is the yttrium iron garnets. The typical thickness of the film is about 20 microns, so it basically the size of the domains is approximately the size of the thickness of the film because of the demagnetization. The saturation magnetization is not that high. It's about 200 Gauss, so it's much smaller than in case of dysprosium, for example. So it's in a very comfortable range for the whole probe. So you don't oversaturate. You don't get out of the ballistic regime and you don't trap electrons in your in the vortices of the magnetic field. And what is good about these samples is the huge uniaxial anisotropy, and this uniaxial anisotropy gives rise to very narrow domain wall. So the uniaxial anisotropy tries to orient the spins either up or down in the domain wall. So the spins are rotating outside of this vertical direction. So the higher the anisotropy, the narrower is the domain wall. And in this case, the domain wall is about 10 nanometers. So it doesn't sound very narrow, but if you consider that the unit cell in those garnets is huge, is about one nanometer, so you have only 10 unit cells within the domain wall, and that will be important in the future to understand the behavior of those of the domain wall motion as we move them by external magnetic field. So the overall arrangement is quite simple. You have this garnet film with the uniaxial anisotropy, so it means that domain on the left is the spins are pointing upwards, in the domain on the right the spins are pointing downwards. In between there is a domain wall, and if we place the whole probe right above of this domain wall right in the middle, then we should measure zero hole voltage because the average magnetic field would be zero. And if we move it left and right, we would be able to see the changes in the magnetic flux, and then as a consequence, so we can track the movement of the domain wall. So that's the typical picture of the hole probe. So you would have several hole probes in one device. So you send current from this contact to this contact, and then you measure hole voltage on several of the hole probes, and then so you can superimpose the picture of the garnet on top, and so you would hope that the domain wall is more or less straight, so then you can convert your signal into the movements of the domain wall. So as I said, in our case, if you deal with the ballistic Hall magnetometry, then what you measure your hole voltage is simply proportional to the average flux. If your domain wall is straight, then what happens? You can easily convert the measured hole voltage into the displacement of the domain wall. And we actually do know that indeed our domain walls are straight, because we can correlate the signal on different hole probes, and we know that we see each of the step on all of those hole probes, and it's only possible if the domain wall is straight. So also maybe to say that you can actually create a variety of these techniques. So you can actually deposit metallic hole probes right on the garnet film, and in principle you can actually measure with the other hole probes as well. But for today's talk, I'll mainly talk on the gallium arsenide, aluminum gallium arsenide hole probes. So what happens if you put your garnet film on top of your hole probe and start to apply external magnetic field? So in most of the field range, it would be straight line, like here at the top, say above 10 ersted. But at certain small area, you would see a number of jumps, and the signal changes quite rapidly. So what happens in this case is basically, you know that at this moment you caught one domain wall underneath of your hole probe, and this hole probe start to propagate under your hole probe. So why do we see why do we see those vertical jumps, not simply a smooth curve? The reason is quite simple, because there is always there are always spinning centers in any magnetic. So, and it can be internal defects like impurities or dislocations, or it can be even like a simple scratch on the surface, which changes slightly the thickness of the film. So there are many different reasons for that. And basically, domain wall, it get pinned on a certain defect, and then you apply external magnetic field. You create a magnetic pressure on the domain wall. At a certain moment, it just jumps away, moves to quite a long distance. And it might, in an avalanche, it might release from some other defects as well. And then it gets pinned on the next one, and then you need to apply more magnetic pressure, more higher fields to depin from the next defect, and so on. So this is quite a well-known effect. It's called Bargausen effects or Bargausen jumps, and it's probably something which is very typically shown on the experiments at school. As you change the magnetization of the magnetics, you don't do it smoothly. You do it through those jumps, and usually you can put a pickup coil and actually listen to those jumps. The interesting part is that you can actually make statistics. How many jumps of different sizes can you get, and this statistics depends on the dimensionality of the system, as usual. So it's a critical behavior. It's a bit difficult to put a straight line in our case, but the most fit is probably the exponent 4/3, and 4/3 should be the dimensionality too. And it tells you that our domain wall actually moves very just as a vertical wall. And actually, at lower temperature, you get maybe a transition from the dimensionality 2 to dimensionality 1, and it tells you that the domain wall actually not only vertical but also is kept straight. So at least on the size of one hole probe. So now let's get to the interesting part. And what happens if we sit within one of those jumps, one of those Barr-Gaussian jumps, and we start to relax the dominant wall by sweeping it back and forth? What happens that the dominant wall will find a very relaxed conditions, and then you will start to observe smaller and smaller Barr-Gaussian jumps, and at a certain moment you would notice that those jumps they start to be equidistant, like on this mini hysteresis loop, and it would be interesting to figure out where these equidistant jumps are coming from. Well, to figure it out, what helps is if we convert. So here is another local hysteresis loop, and it consists of a number of small jumps. So we went up to here, then go down, then go forward, and you can see that those jumps are always so we basically have quantized position for the dominant wall. If you convert this, the changes in the magnetic field into the displacement of the dominant wall, you would find that those jumps correspond to about 1.4 nanometer of the displacement, and suspiciously this 1.4 nanometer corresponds to the period, to the size of the unit cell in a particular crystallographic direction. So why dominant wall now gets pinned to the crystallographic direction and to the specific locations in the crystal? Well, for that we need to look at the structure of the dominant wall. So, as I said, there are two important parameters which describe the dominant wall. It's the exchange energy, which tries to align all the spins in the same direction, and there is a uniaxial anisotropy, which tries to make sure that the exchange energy tries to align the adjacent spins to the same direction, and the uniaxial anisotropy tries to point those spins either up or down. So the size of the dominant wall actually is larger for the larger exchange energy, because it doesn't like too big changes of the angle between the adjacent spins, and it is smaller. The dominant walls are narrower for the large anisotropy. So that's a happy picture for the continuum model. Now let's look at what happens if we have dominant wall which is comparable with the interatomic distance, and you would immediately notice that there are two particular. If you have just countable number of spins, and we said we had about 10 atomic units within the size of the dominant wall, and you immediately notice that there are two particular configurations. One is when the middle spin is pointing perpendicular, and another one is the middle spin is actually, one is pointing up, one is pointing down. And clearly that in the second case, when we have the middle spin pointing horizontally, we have to pay additional energy, and this because we have this spin is working against the uniaxial anisotropy. So the domain wall will try to jump over this configuration and try to be always in this configuration. Mathematically, it's like you can describe it as a Frenkel-Kantorova model, or it's like a Parrell's potential when you have a periodic background potential and your domain wall always tries to sit in such a way that the two adjacent spins are that the middle spin is never horizontal, but the two adjacent spins are one pointing up, one pointing down. So it's it will be impossible to stabilize the domain wall on the top of this potential. It will always jump into the minimum. So it's quite an exciting model. So it's a very well known model, Frenkel-Kantorova, but it's even though it is very simple, it's still very interesting, because so you use the Sine-Gordon equation, which is very simplistic, but you get a lot of interesting excitations, and you can get solitons, and you can kinks and breezes, and in terms of the mathematics, it's quite a rich model despite its simplicity. So, and indeed, for our case, when we have the particular anisotropy and a particular size of the domain wall, we can observe this effect in oh gosh, so it's we're really running out of time, right? And we can see it in our system. So now you can actually go beyond this. You can play a little bit with this domain wall and start to apply external oscillations like AC and measure AC susceptibility. If you start to shake it a little bit in this background Parrell's potential, and if you do it, you find that the basic theory, if you think about your domain wall moving as a rigid object, won't be able to describe the experiment, and it really links us to a very rich, as I said, very rich model of the Sine-Gordon equation when the domain wall propagates not as a rigid object, but it creates a sort of a breezer and then propagates the kinks. So the situation is very similar as if you try to, I'm not sure if you guys can see me or not, if you try to break a piece of paper, if you simply pull it, it's very difficult to break, but if you make a kink, it's very easy to propagate a kink. So, and then you can see the same in the propagation of the domain wall. So, and so it's a very, as I said, it's very exciting area. So it's at the border between very rich mathematics plus very nice technique to measure the domain wall, plus the very good system, which is quite easy to measure. Unfortunately, when we started to work on this, there were in parallel we started to work on the on graphene as well, and that for several years we basically abandoned this topic of the whole magnetometry and the domain wall propagation, and we've been working on a lot on graphene. So, and I realized that the time is running out, so let me just very briefly make a connection to the present days now. So, of course, with the graphene, there are lots of other topics to work on, and you have lots of different exciting properties. this material, which ensures lots of possible applications. So it's very difficult to pick one, and especially to come back to work on the whole magnetometry. But at a certain moment, because what happened that we started to work not only on graphene but on many other two-dimensional crystals, and even further, we started to work on the heterostructures based on those two-dimensional crystals, and this really allows a lot of new devices to be created and studied. So there were tunneling transistors, there are LEDs, solar cells, and so on. So these days we understand really well the combinations which we can create and which we cannot create out of those heterostructures. And interestingly, recently, a couple of years ago, a new class of two-dimensional materials started to appear. Is the two-dimensional ferromagnets, and it turned out to be that there are a lot of possible ferromagnets which we can study. Probably the most popular still these days are those based on chromium chloride, bromide, iodine. And why is it interesting? Why is it exciting to study those 2D ferromagnets? Well, if you look at the three-dimensional case, well, then depending on the spin dimensionality in the three-dimensional case, you would always have a phase transition. So it's very difficult to distinguish between those spin dimensionality, either Ising or the XY or the XYZ, the Heisenberg case. In the two-dimensional case, the situation is completely different, because the proper phase transition exists only for the spin dimensionality 1, and it's the Kosterlitz-Thouless case in the XY, and it's you don't have any phase transition in the Heisenberg case. So that's why it's really exciting it's really interesting to study those two-dimensional ferromagnets, and there are many different ways how you can study them. Carifact is one, tunneling is another one. But to link to our today topic, what I want to promote is the work done recently by Min-Soo Kim in Manchester, where he applied this ballistic hall magnetometry to study the two-dimensional crystal. So, and it's basically you get you do everything exactly the same as I showed to you before. You prepare a Hall probe out of graphene, and you can transfer, you can place, same by hands. Those Gamet films I was placing by hands as well. You can play by hands your ferromagnet on top, and you can apply the whole magnetometry to do it. I should say that the guys in Manchester are so good that they can make those Hall probes reusable. They can deposit your ferromagnet on top, take it away, and put another one, so you can reuse your Hall probe many times. And again, so similar as in the gallium arsenide Hall probes, you can see the domain wall propagation underneath of this underneath of the Hall probe. So those steps are again the domain wall pinning under the Hall probe. This work is only starting. So I would say that so from here we basically extract. So far it's only only at the very beginning. So we didn't pay much attention to the domain wall motion. here at all. So it's mainly was to study the bulk properties like the magnetization of those 2D ferromagnets, for example, as a function of temperature, as a function of thickness. So what you find that the TC of those ferromagnets goes down with the number of layers as expected, whereas the bulk magnetization doesn't, which is the characteristic of the 2D ferromagnets. And it's really, I think it really has, as I said, this the application of this technique to study 2D ferromagnets is only at the infancy. I think that there is a lot of lots of opportunities to study the domain wall motion in those 2D ferromagnets, and there will be a lot of exciting phenomena observed in the future. So I'm really sorry that I rushed through the last part. I will finish here by putting a few conclusions. But most important, let me thank collaborators with whom I collaborated on both topics over the years, and thank you for your attention as well. Thank you.
Thank you, Kostya, for the very inspiring talk. We really start on the right foot here. I learned a lot today. So, folks, if you have questions, please click on the Q&A button and make your questions so I can pass to Professor Novoselov.
Right. So, Antonio, have you seen those crystals before, the beautiful garnet and the graphite crystals?
No, this is really beautiful. No, I didn't see it before.
I think it's something for us to do if we all survive through the virus. So just go into those mines and try to get the garnet and the graphite together.
You're by the way, everybody's listening to you. You're giving ideas to the rest of the world right now. Folks, any questions you'd like to ask Professor Novoselov? Yes, we have questions from, let's see, one here from...
right, so I can actually...
Putra.
Yeah, let me answer this one, and then I can see it, and you can prepare, and you can prepare the next one. Right? So yes, so the question is it possible to create scanning probe on this whole magnetometry? Indeed, it is, and I think there are, and actually there is a company which makes those scanning probes based on the 3.5 semiconductors. It's, I mean, it was reasonably popular to, I think that they made a number of those scanning probes, both for room temperature and for the low temperature as well. The problem, of course, was always that it's a bit tedious to make those probes from 3.5 semiconductors, and especially you can imagine you need to make it on an edge to make the scanning. So it's a very difficult process if you try to do it from the 3.5. But but this company exists. I think it was based in Nottingham at a certain moment, and then it's the Turkey between UK collaboration. I think someone needs to try to attempt to do it with graphene, because it should be easier with graphene. At least you don't have this problem of the depletion lengths, and it might work. It might work better, or at least simpler. But those probes indeed have been used, and that they were used a lot to study vortices in high TC superconductors. So there were a range of very exciting literature on the scanning probes to observe the vortices in high TC.
Okay, next question from Victoria Cornish. you have shown a beautiful picture of domains, and then a figure with different domain shapes depending on the film thickness. Is there an intuitive explanation for this?
Well, I should say that, like many years ago, I indeed developed the intuitive explanation, but those beautiful figures which depend on the thickness, if you excuse me, I won't switch back to my screen. So everybody can see the Q&A, right? Not my screen now, or what is it? Should I share my screen?
You can share your screen.
Yeah, sure. So if I try to go back and if I manage, so those those very unusual domains. There were, I should say, it's not a very usual structure. It's called the undulating domains, and it's a surface effect. It's quite a, it's quite. I hope you can see it. It's quite a particular combination of the uniaxial anisotropy and the thickness, and so typically people try to avoid it. It's a surface effect. It's called wedge effect at the surface. It basically allows you to reduce the stray field, because you always need to close the flux, right? Close the loop. And if you have striped domains, you close the flux in one direction only. If you have those undulating domains, you close the flux in 2 dimensions. So it's quite unusual system. So you really need to get into a very specific range of parameters to see it. But in principle, there is nothing else. So you only put the uniaxial anisotropy and the in-plane anisotropy as well, and the exchange. And with those 3 parameters, you can get those any of these pictures.
Okay, next question from Ren Lim. Hello, Prof. Is there a chance of functionalizing 2D ferromagnets so they can stick to biomolecules?
Well, the answer is probably yes. I'm sure that we can. The problem is more severe, though. That I understand where you're coming from. So you're lots of, and especially in the coronavirus, so lots of proposals now how to functionalize certain chemicals, stick to biomolecules, and then collect them by a magnetic field, for example. In principle, you can functionalize the 2D ferromagnets. The problem is that so far we haven't got ferromagnets which show robust ferromagnetic properties at room temperature. So I think the major direction, one of the major direction now, is to get 2D ferromagnets which are still ferromagnetic at room temperature, and then we can play with the functionalization, which is definitely possible.
Okay, next question from Iana Veipravova. Thank you very much for a very interesting talk. Actually, we're just measuring a spin chain using the same technique, happy face. May you comment on the linearity of the graphene-based Hall probe in the magnetic field range up to a few Tesla? The step-like artifacts are quite common on the commercial and conventional micro Hall probes. Thank you.
Yeah, so of course, I mean, the problem with any Hall probes would be that in a few Tesla field you get into the quantum Hall regime. So and this ballistic story works only on the within the very small field when the cyclotron radius is smaller than, sorry, is larger than the size of the Hall probe. So beyond that, you start to get changes in the Hall. There are several steps which are associated with certain trajectories within the Hall probe, and at the end of the day, you get into the quantum Hall effect. So difficult to advise anything. Maybe I can say that you can try to put the whole probe parallel to the fields, but then it still requires a lot of alignment. So if the conditions in your experiment allows you to put the whole probe parallel to the field and still play with the spin chains as you described them, that might be a solution. But indeed, several Tesla in the perpendicular field, it's a quantum Hall effect already. So.
Okay, so last question from Saroj Dash. Thank you for the excellent talk. Question: in the graphene Hall magnetometer devices, if graphene is encapsulated with HBN and chromium bromine is on the top of the HBN, how the magnetometer efficiency changes with top HBN thickness? So it's about the thickness of the HBN.
Right. Yes, so that's correct. So you try to encapsulate with HBN. So in Minsu paper, it's there is an estimate of the influence of the HBN on the measurements, but I can say that it depends on the effect which you are studying. But as long as the thickness is smaller in comparison with the size of the crystal or the size of the domains, actually, it doesn't really matter. If the thickness, and that's typically the case. We know that the size of the domains in those crystals. So there is quite a literature both from Seattle and from MIT. The size of the crystals is few microns, and the thickness of HBN is few nanometers. So you are pretty much always in the safe regime. So as long as the thickness is much smaller than the domain size, it does matter.
Okay, we have a few minutes, so last question from Adrian Nixon. Thank you for a fascinating talk. A basic question: could you tell us why you choose to use graphene as the material for the Hall probe?
Well, the reason to choose graphene is quite simple. So first we can. Second, it's actually it would be stupid not to use this opportunity, since we can create the heterostructures out of those materials. So it would be really, it's kind of natural that you have the measurement system in close proximity to your object which you are trying to study. I think it's great opportunity. But also what is important for the ballistic Hall magnetometry is this ballistic part. And in gallium arsenide, for example, because of the optical phonons, the mobility degrades extremely fast above 50 Kelvin. So you lose your ballistic properties very, very fast. In graphene, because of the very high Debye temperature, it's very stiff lattice. You still have ballistic properties up to very high temperatures. So it's natural that you want to switch from 3.5 into graphene for this application.
Okay, so we are already on the top of the hour. I want to thank Professor Novoselov for, again, fantastic talk. I want to thank everybody around the world who watched this today. I wish you good health, be safe, and I see you next week for another chaos seminar. Take care,
Great.
folks.
Thanks a lot, guys.
Bye-bye.
Thanks so much.
Thank
Bye.
you, Kostya. Thank you.